Hello and welcome to 2.5 Limits Involving Infinity. Okay, so in this section we investigate the global behavior of functions and in particular whether their graphs approach asymptotes, vertical or horizontal. Okay, infinite limits. Okay, so in the previous section we saw that the limit as x approaches 0 does not exist. Okay, one of the reasons for that is as we get very, very close to 0 from both sides, we see the vertical asymptote appear. Right? So we have a vertical asymptote at x equals 0, and f of x just grows out of control as we get closer and closer to 0. And you guys will see as we get very, very close to 0, our function gets really, really huge. Okay, so we see that as we approach 0, our function goes to infinity. Okay, so symbolically we could say the limit as x approaches a of f of x equals infinity. Okay, so this notation means that the values of f of x can be made arbitrarily large as we please, by taking x sufficiently close to a on either side of a, but not equal to a. Okay, so another notation would be f of x approaches infinity as x approaches a. Okay, so just remember infinity is not a number, but the expression equals infinity is often read as the limit of f of x as x approaches a is infinity. Okay, or we could have any of these other versions. Okay, so in this diagram we see that at x equals a there's a vertical asymptote, and again we have the function approaching infinity as x approaches a. Okay, likewise, if we have a vertical asymptote and we see the function is going infinitely in the downward direction, we could say that the limit as x approaches a for the function is equal to negative infinity. Okay, implying that it's going, values of f of x are getting to be very large in the negative direction, okay, as the function gets closer and closer to a. Okay, so symbolically, limit as x approaches a of f of x is equal to negative infinity. Okay, another way to say it, f of x decreases without bound as x approaches a. Okay, we could say similar things for the one-sided limits. Okay, limit as x approaches a from the left, limit as x approaches a from the right. Okay, so we see some cases if we're doing the one-sided limits. Okay, limit as x approaches a from the left, okay, it's going to infinity. Limit as x approaches a from the right, it's going to infinity. Limit as x approaches a from the left will be negative infinity. Limit as x approaches a from the right will be negative infinity. Okay, and by now we know that we have a vertical asymptote. Okay, now we consider it a vertical asymptote if at least one of the following statements is true. Okay, so if that limit of the function okay, is going to go to infinity, right, as x approaches a in general, or x approaches a from the left, or x approaches a from the right. Okay, the function will be infinity. We have a vertical asymptote. Similar thing in the other direction. Okay, you'll have, if the function is going to negative infinity, as x approaches a, then we have a vertical asymptote that way as well. Okay, so example 1, evaluating one-sided limits, one-sided infinite limits. Find the limit as x approaches 3 from the right, and find the limit as x approaches 3 from the left of 2x over x minus 3. Okay, so let's take a look. Let's take a look at the graph. Okay, so if we look at the graph, okay, of 2x over x minus 3, okay, so we see that the limit as x approaches 3 from the left of our function, we're approaching 3 from the left, so it looks like we're going infinitely in a downwards direction, so that's going to be negative infinity. Okay, if we do limit as x approaches 3 from the right of our function, then we will have, if you look at 3 from the right, this is going to approach infinity. Okay. So two familiar functions whose graphs have vertical asymptotes are y equals ln x and y equals tan x. Okay, so looking at the graph of ln x, we see that the limit as x approaches 0 from the right for ln x is negative infinity. Okay, so we're just going to approach negative infinity. Okay, so just remembering that ln, the natural log function, okay, same thing is true for y equals log base a of x, as long as a is greater than 1. Okay, let's take a look at the tangent function. So here we have the graph of the tangent function. Limit as x approaches pi over 2 from the left, okay, is infinity. Okay, so let's take a look at pi over 2 as we approach it from the left. We have infinity. Okay. As we approach pi over 2 from the right, we go to negative infinity. Okay, so we have asymptote. Okay, so in fact every pi we have a vertical asymptote. Okay, and we can describe the vertical asymptotes with these equations, right? With this equation would give all the vertical asymptotes. Okay, x equals 2n plus 1 times pi over 2. Okay, let's take a look at another example. Find the limit as x approaches 0 of ln of tangent squared x. Okay, so we know if we had ln x and x is approaching 0, we'd have negative infinity. Right, so let's take a look. If we had t, let's say t is equal to tangent squared. Let's declare a variable t. then we would say that t is greater than or equal to 0 and so for this to work, right, we would say tangent squared, if we plug in 0, right, think of it this way, if you're plugging in 0 into here, right, you have tangent squared of 0, which is 0. Okay, so you have basically limit as x approaches 0 of ln of 0. Okay, once you plugged in the 0 there into the x, you got tangent squared of 0, which is equal to 0. And now ln of 0 okay, so if we have that, then we basically have ln of 0, and we know that this is going to go to negative infinity just from our discussion of our previous problem, right, when we had ln of x, limit as x approaches 0, right, this one went to negative infinity. Okay, so that's the case with this one as well. Okay, this one will also go to negative infinity. Okay, limits at infinity. Okay, so in this problem, so here we're looking at what happens to this function as x becomes very large. Okay, and we could always say that as x becomes large in the positive direction or in the negative direction. Okay, what happens to the function? Okay, so if we look at a table and if we look at a graph, this is what happens as x becomes really large. Okay, so when it's 0, okay, we get negative 1. If we plug in 1, we get 0. And then as we get larger and larger in the x direction, look at what happens to the y's. Okay, where they get arbitrarily close to 0.999998. Okay, looks like it's going to get arbitrarily close to 1. Okay, so we would say that the limit of this function equals 1. So now how do we show this? I want to show you guys basically the technique we use. If the top and bottom degree are the same, okay, generally we take the coefficients, turn it into a fraction, and that becomes our limit. Okay. Another way to show this is if we took each term and divided it by x squared. That will also help us to visualize what's going. It's almost like a reducing of sorts. Now the limit as x goes to infinity, so if x gets really big in this fraction, we have 1 over infinity, which is basically 0. Right, we would go to 0 there. That would approach 0. 1 over something really large, that's going to approach 0. So here we have x squared over x squared, which would reduce to 1. This one would also reduce to 1. We get 1 over 1, which is 1. Okay, so in general we use the notation, okay, limit as x approaches infinity of f of x equal to some limit. Okay, let f be a function defined on some interval a to infinity. Then the limit as x approaches infinity of f of x is equal to a limit. Okay, another notation. F of x approaches the limit as x approaches infinity. Okay, again, the symbol infinity does not represent a number. Think of it as if you're going to be putting in really large numbers in there, right? We will never get to infinity. We will just try to approach infinity. Okay. Limits at infinity. So just some graphs, various graphs here. Okay. It looks like these functions are approaching a particular value as we go to infinity. Okay, looks like we're approaching what's called a horizontal asymptote. Okay, so the function's approaching some value. And notice for horizontal asymptotes, a lot of times you can cross horizontal asymptotes, and it's not always the case with vertical asymptotes. Okay, you could cross over the asymptote, and it's not a problem. Okay, looks like this one's approaching some value going into infinity. Okay, so for that earlier example we did, looks like this is approaching y equals 1, and that would be our horizontal asymptote. Okay. Okay, so if we're going in the negative infinity direction, okay, this function appears to be approaching some value, L, same as this one. Okay. Okay, the line y equals L is called a horizontal asymptote of the curve y equals f of x if either limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x also equals L. Okay, and we discussed that y equals 1 is the horizontal asymptote for this function. Okay, here's a figure. If you look at y equals f of x, as x goes to infinity, okay, it has approaching negative 1 going to the right. Okay, so it has two horizontal asymptotes. And then going to the left, it's approaching y equals 2. Okay, so this one happens to have two different horizontal asymptotes. Okay, so let's take a look at this example. Find the infinite limits, limits at infinity, and asymptotes for the function f whose graph is shown in figure 12. Okay, so same figure, let's take a look. Alright, so we have our x-axis is here, y-axis is here. So make it a little darker. Alright, so as x goes to, okay, so look at here, as x approaches negative 1, so limit as x approaches negative 1, right, it appears we have our function is going to infinity. Okay, it appears we got a vertical asymptote there. Okay. limit as x approaches, let's go in a negative direction. As x approaches negative infinity, okay, so that implies we're going to go infinitely to the left. Looks like it's going to approach the value of 2. Right, so it's tapering off, right? It's coming down like this, it's tapering off. So it looks like this would be equal to 2. And then limit as x approaches infinity. So going to the right, it appears this is approaching 3, 4. Okay, and then there's one more we didn't discuss. We got another, looks like an asymptote, vertical asymptote here at x is 2. So we'll do limit as x approaches 2 from the right. That would be approaching infinity. And then limit as x is approaching 2 from the left. From the left, it's going to go downwards. So that would be negative infinity. It's going towards negative infinity. Alright, any questions on that? Just bring it up in class or email me. Okay, let's take a look at limit as x approaches infinity of 1 over x, and limit as x approaches negative infinity of 1 over x. Okay, so just remember what happens to 1 over x if we looked at the graph of it. We would see that 1 over x looks like this. So as x approaches infinity, right, we're going to be approaching 0. Okay, you could also look at this in terms of a table value. Right, when x is 1, we get 1, but when x is 10, we get 1/10. When x is 100, we have 1 over 100. Okay, so it looks like very drastically we're approaching 0. Okay, so limit as x approaches infinity. And then limit as x approaches negative infinity. Okay, similar idea. Now you have, let's say, negative 1, negative 1. But if you do negative 10, now you have negative 1/10. Negative 100 would be negative 1 over 100. Okay, so that'll also be approaching 0. Okay, so we got a horizontal asymptote at y equals 0. Okay, so we see that if we do limit as x approaches infinity of 1 over x to n, as long as n is a positive integer, that limit would be equal to 0. Okay, whether you're going in the positive infinity direction or negative infinity direction. Okay, so that previous example basically outlined this rule, this important rule for limits at infinity. Okay, so anytime we get limit as x goes to infinity of 1 over x, or it could be 1 over x squared, 1 over x cubed, right? That bottom, that's going to go to infinity. That means that denominator is going to grow very fast. And when you have just a fixed number, 1 over something getting bigger and bigger on the bottom, that limit will go to infinity. Okay, quotient of functions that become large. So limit as x approaches infinity of this function. So let's take a look. Okay, so we got limit as x approaches infinity. And so what we're going to do is, whenever this is the case, we're going to take every term and we're going to divide by the highest degree term. Okay, so the highest degree term is x squared. Okay, and this only works in this case when degree of the top matches degree of the bottom. Okay, you just divide every term by x squared. Okay, so we would have limit as x approaches infinity 3x squared over x squared minus x over x squared minus 2 over x squared over 5x squared over x squared plus 4x over x squared plus 1 over x squared. Okay, so now look at what happens. We have here limit as x approaches infinity. So for this term, 2 over x squared, as the x goes to infinity and you're squaring it, this is going to go to 0. Okay, so will this one. This term will also go to 0. Now you could do some reducing here for these other ones. This would reduce to 1 over x. Okay, but 1 over x, that follows the same pattern as these other two. Right? As x goes to infinity, this denominator will go really, really large. This will go to 0. And then here, this would reduce. We have 4 over x. So this is going to go to 0. Okay, so that will go to 0. These would cancel. X squared and x squared would cancel. Okay, so we're left with 3 over 5. Okay, and that would be the final answer. Let's take a look at another example. Compute the limit as x approaches infinity of square root of x squared plus 1 minus x. So in this case, it'll be a little difficult to figure out what happens here. If we plug in infinity, right, as x gets really, really large, it'll get squared, and then you'll take the square root minus, again, another number that gets really, really large. So it's a little difficult to figure out what's going on there. So what we have to do then is use a technique to try to get the limit in a different way. Okay, so we would say x approaches infinity. Okay, we have the square root of x squared plus 1 minus x. And then just multiply top and bottom here. So we're going to multiply by the conjugate of this, treat it like it's a numerator. Okay, so we're going to multiply by a square root of x squared plus 1 plus x. Okay, over square root of x squared plus 1 plus x. Okay, so by doing that, we could FOIL the top, put this over 1 if it helps you to visualize it. Okay, FOIL the top, so you'll have square root of x squared plus 1 times square root of x squared plus 1, which will just turn into x squared plus 1. Okay, then we have negative x times positive x, so that'll be negative x squared. And then the bottom, you have 1 times x squared plus 1, square root of x squared plus 1 plus x. Okay, x squared and then minus x squared, that's gone. So we can combine those two like terms. They disappear. We're left with 1 over square root of x squared plus 1 plus x. Okay, so limit as x approaches infinity of 1 over square root x squared plus 1 plus x. Okay, so now notice what happens now if x were to be plugged in here. As x gets really, really large, right? You have really, really large. You have something like a 1 on top that's fixed. And then you have the square root of x squared. So this one is going to act basically like an x with a little bit of extra hanging off of it. It won't make much difference in the long run. Think big picture here. Okay, if you have the square root of an x squared, this is basically like an x, right? With a little tiny piece extra. Okay, so this denominator is going to grow. You have basically 1 over x plus x. It's like a 1 over 2x. That's going to grow exponentially. Okay, so that means 1 over something really big. This is going to be 0. Okay, for a natural exponential function, y equals e to the x. Okay, notice the graph. Okay, we have a horizontal asymptote at y equals 0. Okay, that's because if we took the limit as x approaches negative infinity, that would be equal to 0. Okay, and it approaches 0 very rapidly if you start plugging in values going to the left towards negative infinity. Okay, you'll notice it gets very, very close to 0 at negative 10. And it'll keep getting closer to 0 as you go farther out towards negative infinity. Okay, evaluate the limit as x approaches 0 from the left of e to the 1 over x. Okay, so as x is approaching 0 from the left, we could let a variable equal to 1 over x. Let's say t equals 1 over x. Okay, and we know something about 1 over x, right? As t, just remember what happens to that function 1 over x. As t goes to negative, we should say that as x goes to 0 from the left, let's do it this way. Limit as x goes to 0 from the left of 1 over x, this would go to negative infinity. Okay, so here basically we have our t is going to go to negative infinity. Okay, so if we have t going to negative infinity, and we have e to the t, okay, we could rewrite that as saying we have 1 over e to the positive infinity. Okay, and that's going to get really, really large, right? So we have 1 over something really, really large. The limit for that will just turn to 0. Okay. The limit as x approaches infinity of sine of x. Okay, so remember the sine curve. Okay, sine of 0 is 0. So this is going to keep going like this forever. Right, and it'll oscillate between 1 and negative 1. Okay, and because it'll just keep oscillating between negative 1 and 1, negative 1 and 1, the limit as x approaches infinity of sine x does not exist. Okay, infinite limits at infinity. Let's take a look. The notation limit as x approaches infinity of f of x equals infinity is used to indicate that the values of f of x become large as x becomes large. Okay, similar meanings are attached to the following symbols. Okay, so here we have some figures. Okay, here we have e to the x. So as x goes to infinity, notice that we have this function take off in the infinity direction. Okay, so that's infinity. As x goes to infinity for x cubed, we have a similar story. Right? It takes off in infinite direction. If we had limit as x approaches negative infinity, now we're going in the opposite direction. So we're going to negative infinity. Okay. If we did a comparison of e to the x with x cubed, okay, notice e to the x, it just shoots up faster. Okay, e to the x becomes large as x goes to infinity at a much faster rate than y equals x cubed. Okay, notice the sharper turn upwards for e to the x compared to x to the third. Okay, and that's going to be a lot of times the case. If you have an exponential function versus a cubic function, the exponential function is going to definitely increase at a faster rate. Okay, find an infinite limit at infinity. Okay, limit as x approaches infinity of x squared minus x. Okay, this is a quadratic function. You could graph it and take a look at what it becomes. You could also do is you can factor out an x. Okay, you could say this is x times x minus 1. So basically you have infinity times another infinity, right? You have something really large times something really large, which will also be infinity. Okay, you got to think big picture here as x goes to infinity. And then let's take a look at this one. We have x squared plus x over 3 minus x, limit as x approaches infinity. So to solve this one, we divide top and bottom by the highest power of x that occurs in the denominator. Okay, so you want to almost do like a reducing of sorts. You want to divide everything by the highest power of x that occurs in the denominator. Okay, so we would have limit as x approaches infinity and now highest power of x that occurs in the denominator is x, so divide everything by x. Okay, so this one would reduce to 1. X over x, that would reduce to 1. 3 over x, as x goes to infinity, as this gets really, really large, this is going to go to 0. And then x squared over x, that would reduce to x. Okay, so we have x. Let's do it this way. I'll go down here. Limit as x goes to infinity of x plus 1 over 0 minus 1. Okay, so you have, as x gets really, really large, this will go to infinity. Right, so the top part will go to infinity. And then the bottom one will become negative 1. So you have infinity plus 1, which is basically infinity over negative 1. You kind of have a positive over negative scenario, so this is going to go to negative infinity. Okay. Any questions, just email me or bring it up during class. Have a good day. Have a good night. We'll see you soon.